Welcome. This is Small Head, Big Problems. I'm a small head and I've got big problems. So I'm finishing the 2016 paper today. We only have question 19 and 20 to go. Hope you enjoyed this series. Can I start with a bit of shameless self-promotion? I am a private math tutor. This is what I do. It's how I make a living. And yeah, I offer very competitive rates, especially compared to if you find me with an agency and stuff and they take a big commission. So if you are looking for a private tutor and you like my teaching style, then please do send me a message. The details are in the description. All right, let's get started. Again, no preparation, haven't seen these questions before. This video series is not about giving you some polished video solution, like where I've like thought about the question and done it twice and had I look at the solutions and blah blah. No, um, I'm trying to demonstrate how to pull yourself up by your bootstraps, how to think on the spot, um, how to make mistakes and hopefully correct them and learn along the way. So let's go. All right, let's do it. So, um, question 19, the coefficient of x cubed in the expansion of 1 plus 2x plus 3x squared to the sixth power is equal to twice the coefficient of x to the 4 in the expansion of 1 minus ax squared to the fifth power. Okay. Find all possible values of the constant a, all these options. Right. So, yeah, that's not too bad. I mean, we use the binomial theorem, obviously. Let's maybe start doing our little Pascal's triangle on the right, get our coefficients in place. 1, 4, 6, 4, 1. So that's the fourth power. 10, 10, 5, 1. That's the fifth power. And finally, we will need the sixth power. 15, 20, 15, 6, 1. Cool. Um, why don't I start by warming up with this one? It's just a lot easier. We're interested in the x to the 4 coefficient. Um, you could find that directly, without doing any sort of full expansion. But let me just kind of, you know, give you the first few terms so it's a little bit clearer. So the first term is just 1, right? This one, yeah. And then the second term would be minus, well, okay, let's see, plus 5 times 1 to the 4, so 1 to the 5, times 1 to the 4, times minus ax squared, yeah? And then we have plus 10 times 1 cubed times minus ax squared to the second power, and so on and so forth. So if you know your binomial expansion as well, you don't really need to put all that. Obviously, all the ones are, just simplified to 1. 1 to the anything is just 1. And then the fact there's a minus here gives us an alternating sign. But whatever. So we're interested in x to the 4 component, which you can see is going to be this term, right? This term is quadratic. This is the fourth power. The next one will be to the sixth power, and so on. So that's going to give us just 10a squared x to the 4. That would be the fourth power term in there. So the coefficient is 10a squared. Okay. Now for the kind of the big boy. There are some interesting ways of doing this a little bit more directly, but the way to do it sort of, yeah, let's say more um, using the binomial theorem, like the standard binomial theorem, would be to bunch these two things up, for example, into a single term and consider it the sum of these two terms and expand it to the sixth power. We are interested in the cube one, and I'm thinking it'd be good to like bunch it up this way rather than this way, a little bit more simple, because when this is sort of squared, that's going to already give us an x to the 4. So basically, we won't even need to consider a later than the square term. So I mean, let's go. So first we have just 1 plus 2x to the sixth power plus 6 times 1 plus 2x to the fifth power times 3x squared to the first power. And then basically a bunch of stuff that we don't care about because after that, I'm going to have a term of 3x squared to the second power. So everything's going to be at least order 4 or more, right? So it's not going to contribute to the x cubed coefficient. All right, cool. So basically, I'm only concentrating on these two terms. So I want the x cubed coefficient. So I just want the x cubed coefficient of this one, which is going to be, 1 cubed times, well, let's see, wait, so this is going to be the linear square quadratic. So we need this binomial coefficient, right? This would be a cubic one. So 20 times 1 cubed times 2x cubed would be the x cubed term in this one. The x cubed term in that one, well, let's see. So we have 3x squared. So I'm interested in the linear term in this one. So it'll be, okay, 6 times the linear term in this one, which is 5 times 1 to the 4 times 2x to the 1, and then times the 3x squared. All right, that's going to give us the cube term. Okay, so it's going to give us 80x cubed here. And we have 30 times 2 is 60 times 3 is 180 x cubed there, if I'm not mistaken. Let's hope so. So 260 x cubed in total. Cool. So I'm just gonna set these equal to, sorry. Coefficient of x cubed in this is twice the coefficient of x4 in that. Okay, so 260 x cubed equals 2 times the 10a squared. Cool. So I can divide by 20. Sorry, I should put x cubed to just 260. 13 equals a squared. So a is plus or minus the root of 13. I mean, that doesn't seem to work out. It's none of these options, and I can't simplify it anymore. Oh, that's annoying. So what gives? Uh, okay. I mean, this seems pretty normal. Surely I made a mistake here. Coefficient of x cubed. Yeah, what am I doing? See, always these silly calculation mistakes. This would be 160 x cubed, and then 340. Yeah, I feel like I'm rushing a bit too much, making too many silly mistakes. So 160, so 340. Okay, which means divide by 20, that's 17, and divide by, and yeah, so plus or minus the square root of 17. So hopefully answer B, and I'm gonna have a look. Okay, not too bad, not too bad. Next one. Maybe need to zoom out a bit. Okay, the diagram shows a square-based pyramid with base PQRS and vertex O. All the edges of the pyramid are of length 20 meters. Okay, all the edges, okay. That's 20, 20, 20. These are all equilateral triangles, basically, in a square. Okay. Find the shortest distance in meters along the outer surface of the pyramid from P to the midpoint of OR. The shortest distance in meters along the outer surface of the pyramid. Surely they don't mean just the distance. Would that mean the shortest distance? Oh, but along the outer surface. Oh, okay. Nah, they could have expressed this a little bit nicer. Um, okay, I understand. So, um, yeah, yeah. Um, okay, sorry. But so basically, it's kind of like if you're an ant, right? Walking along the surface of this pyramid, what's the fastest way of getting from P to the midpoint of OR, right? So what's the shortest kind of curve along the outer surface from P to OR? Right, okay. I see the kind of thing. So do we need to go to do this? Do we need to kind of go here and go and walk up? Do we need to go whoop, along like along here and here. Yeah, that's interesting. So I have done these kinds of things before, with a cube and stuff like that, right? This kind of this classic problem of a, you have a cube and you're an ant and you want to go from here to here and what's the shortest way? And it's definitely not by going along the edges like this, right? It turns out it's kind of by going along here and here. Um, yeah, and the way to do that, the way to see that is to basically um, create a what do you call it? A sort of basically like flatten the cube, right? Um, so it kind of looks like, yeah. And so you can see there what the shortest distance is because you will be walking in a straight line towards it, of course, right? The straight line in flat space is the curve of shortest length from one point to the other. Um, so if you imagine just kind of cutting along, probably you want to cut along a surface that you're probably not going to walk on, right? Um, or walk along, walk through, uh, probably like this, right? Like why would we go up there? Why would we cut along there? Seems to be counterproductive. So, what's it going to look like? So imagine cutting there and maybe somewhere else, I guess. I guess we can cut here as well. We'll need to make some cuts. Yeah, even cut here, right? Like I'm probably not going to go through here. Um, then yeah, that seems to work. Probably cut here as well. Yeah, because we kind of need like we can't keep it stitched. Right? We only need like one edge of the square still attached, and that's probably the edge we might go through. I think given the symmetry of the whole picture, it's sort of doesn't matter too much, but yeah, it'd be good to get that right. Um, and then yeah, just flatten it. So what's that going to look like? Well, we need to figure out those angles, but those angles are 60 degrees. Okay, so basically, if you cut it and flatten it, right? Obviously, kind of like these edges are still stuck together. Then you're gonna get like this kind of like set of four triangles stuck together, and the kind of total angle there will be the sum of these four angles. So since they're all 60 degrees, it's gonna give us like a 240 degrees. So like 240 degrees is something like this, right? 240. Um, and yeah, basically a bunch of these equilateral triangles stitched together. I suppose, yeah, like should have some like this. Doesn't have to be perfect, but it's better if it's good. Okay, I'm pretty happy with that. Um, and so that's O, right? That's the point O. Um, the point P, so I would have cut it along here. So that's the point P, right? And then going along, we have and that's Q, and then kind of going along like yeah, is it? Wait, I'm sorry. No, I'm sorry. This yeah, I mean this is the point P as well. Like we would have these two there would have been attached. We could even like often people put these arrows, so it would have been attached like this. Um, this is kind of the point P again. This is the point Q, R, and S. Okay. And so the midpoint of OR is here. And so yeah, I think I've done my picture well because I can see here the straight line like this. So basically, yeah, like kind of my intuition was we would go along here, and there's kind of a pretty good reason for that. It's sort of like you want essentially like the curve that has the least curvature, right? Like if it has because if a curve is very curvy, then it links two points in like not a very efficient way, right? You want the curve to be as straight as possible. That would be like the shortest one, and you want the curvature to be as little as possible. And that seems to kind of be good because it's kind of like the curvature around that corner is not that much. Like the angle between these two um the faces, the triangular faces of the pyramid are rather small versus kind of like the angles between um the base uh and the triangle faces. So yeah, okay, so we just need to basically figure out this distance. So I'm working inside this sort of yeah, this this quadrilateral. I know this is 10. I know this is 20. I know this is 120 degrees. So yeah, can I use like some kind of cosine rule? I suppose, right? Cosine rule, sort of pretty straightforward, right? So c squared equals a squared plus b squared minus 2ab cosine c. Maybe there's a more elegant way, but I'm gonna go with that. 10 squared plus 20 squared minus 2 times 10 times 20 times cosine of 120, which is 100 plus 400 minus 40 times the cosine of 120. It's cosine of 120. So 120 is here, right? Yeah, that's root. I'm sorry, I keep making this mistake just like yesterday. That's just a half. No, yeah, yeah, it is. Well, minus a half, right? So minus half. So we got 500 minus 20, 480. Okay, so C would be the square root of 480. Which let's see, what's the biggest square factor? I mean, I can take out a 4, so 120. I can take out 4 of that again, out of that again. Um, ooh, I'm seeing it's not looking good. Oh yeah, oh my God, I keep making these really stupid mistakes. Plus 20. That's not looking good, is it? Hmm, because I see a lot of 10s. I can't get a 10. It's not a multiple of 100. Hmm. Oh yeah, that's because so stupid. It's not 40, it's 400. Gosh. Um, ah, I need to calm down. Okay, so that's plus 200, so that's 700. Okay. Okay, yes. So, stupid Zoom thing. So, square root of 700. I can take out a factor of 100, so that's 10 root 7, which is answer D. Oh, please tell me that's correct. Please tell me that's correct. Yes. Awesome. Hmm. Uh, oh, okay, so that's interesting. So there are several options. You could go through the square. Oh, that's interesting. So the solution kind of considers these two nets. So the way I've cut it, the square would be um, would be here, right? Attached to the edge SR. So this is P as well, right? And this is Q, right? So these edges are connected like this, and these edges are connected like this. So the point P is there. So basically you could walk over there. Yeah, could walk over there. This one obviously symmetric, so it's the same. I was a little bit lucky because I kind of picked, the shortest of the two paths. From the picture, it does seem like that one is the shortest. It's not hard to kind of calculate the length of these two paths through the square or through the triangles. But yeah, I just had a feeling basically that that path was going to be the shortest because we're sort of kind of turning a corner that's not as sharp. That's it. Um, I'm just wondering whether there are other ways to consider it. Like, are there any other like straight paths? It's a bit hard to fathom, but like you could like kind of go. yeah, you could kind of go like PQ, like through QR, right? Through QR, and then go here. But that would be essentially the same as that kind of from square to triangle path, right? So there are other paths of the same length, right? But there's kind of these two types through the just the triangle faces or the square faces. Yeah, I don't know. It's interesting. I'm not super like used to working with these types of things, so yeah, let us know in the comments if you have an even nicer way of thinking about it. That's it. That's the 2016 paper done. Thanks for listening. I hope it was useful to you. Please like and subscribe. Give me a shout if you want some private tutoring, and that's it. Thank you so much. I'll see you later.